This video will be an introduction to bucket problems, and bucket problems are also called in and out problems by the AP community sometimes. In and out. Burgers. They are also called integrate a rate problems. And to help you remember that, you're integrate the rate. Alright, so here's how it works. Here is a bucket. And this might either be a real bucket in the problem or a metaphorical bucket. And we'll talk about what that could mean. And the bucket has some amount of water or stuff in the bucket. And then there are usually two rates given. The first rate is the rate in, and the rate in is how much stuff is being added to the bucket. So in this case it would be like, how much water are you pouring in the bucket? Or is rain going into your bucket? Or something like that. And then, let's say that there is a hole in the bucket, dear Liza, and water or stuff is leaving your bucket at a rate out. So we're going to use calculus to answer some questions about, does the amount increase or decrease? Or what is the total amount? Or other questions that we can answer. So here are, this video is basically a huge slew of, I'm not going to say formulas, but sort of concepts of how you can apply the tools of calculus, i.e. derivatives and integrals, to answer a lot of questions. One thing to help you is that usually the word total in a problem will eventually involve using an integral, because the total is sort of like the sum or the accumulation of something. Let's get started. So the first thing that we can find is we can find the total amount added, and that's sort of also the total in, we can call that the total in, between time times A and B. Okay, so the total amount added between A and B is, well, it's the total, so it's the integral, and then it's the total added, or total in, so it's going to be the integral of the rate in. Well, that's not too bad. These are going to be dt because our rates are with respect to time, and we're going to go from t equals A to t equals B, and those will probably be specified in the problem. Cool. We can then go ahead and say, well, the total out, or the total removed, is going to be the integral of the rate out, dt, from t equals A to t equals B. Okay, and notice that the rate in and the rate out, those are going to be functions of t for the most part. And there are going to be four main tools that you have for evaluating these integrals. So the first is going to be the actual integral rules. So let's say your rate out is like 3x, then you would integrate 3x to get 3x squared over 2, and then evaluate from A to B. More commonly, though, for AP purposes, you will have a calculator. Oh boy. And we, in this video, will talk about how you would use your calculator to evaluate some of these integrals. Just kidding, we're going to do that in an example video, but for the most part, you would use a calculator. 3, if you had the area, if you had graphs of the rate functions, and those rates, and that graph had like specified area that was geometric, then you would actually find the area because the integral is the area. And then fourth, and less exact, but if the area was given to in a chart or table format, then more often than not you would be using a Riemann sum to approximate the value of the area. But almost always it will be fairly obvious which thing to use. If you have a calculator, which most of these problems are calculator, then you would use your calculator. If not, then you'd either have an integrable formula, or a graph with area, or a chart. Cool. So we have these two concepts of the total in and the total out, and using these two I can get a formula for the total amount, at time t. And maybe we'll call this t2. And so the total amount at time t2 is going to be, well, it's going to be the total in minus the total out. However, this is missing a key thing, because if I told you that at the end of the month I had made $10,000 and I spent $4,000, and the question was, how much money do I have in my bank account? You can't answer that question unless you know something else, and that something else is the starting value or the start amount of how much you had. So if I told you, hey, at the beginning of the month I had $50,000 because I'm a teacher and I'm rolling in it, then you would say, oh, then I would add my 10,000 and I would subtract my 4,000, and so my final amount would be $56,000. Oh man, I wish I had that much money. Yeah, so what we're going to do is we're going to take this equation and calculasize it, okay, because that's a fairly not too bad concept to understand, that the end amount is the start amount plus the total in minus the total out. And in calculus, that's going to be, well, the amount, or the end amount rather, is going to equal the start amount plus the integral of the rate in dt from t equals the start time to t2, yeah, we call that t2, minus the integral of the rate out. And that integral is also from the start time to the end time of t2. And this is going to be a pretty useful formula for determining the final amount. Now, if you notice, these two integrals do have the same limit, so if you wanted to, you could combine this to be one big integral of the rate in minus the rate out. And that's okay, but through my lots of experience in teaching this stuff, most of the time these are going to be different formulas and you're going to get them in different ways, so oftentimes it is easier just to split them up as two separate integrals. That being said, this quantity here, this idea of the rate in minus the rate out, we can call that something, and we can call that the net rate. Notice I'm going to call it the net rate and not the total rate, because total would imply integral, whereas net sort of implies what's the difference between the two, what's the difference between the rate in and the rate out. And so now we can actually answer a few questions. So for example, I can tell the answer to this question is the amount increasing or decreasing at a certain time. Okay, well, how do I tell if the amount is increasing or decreasing? I would look at the net rate. Oh boy. Because if the net rate is positive, then this implies that the rate in is bigger than the rate out. Okay, if you think about your bank account, again, as a bucket, if you make more money than you spend, then your net rate of money accumulation is positive, and therefore the amount would increase. So this is, if the net rate is positive, then the amount will increase. Okay, and contrary, if the net rate is negative, that is, if the rate in is less than the rate out, then this implies that the amount, the total amount that you have, will decrease. Cool. Also, I think this is the if and only if, or vice versa. So you could either look at the net rate and see if it's positive or negative, or you could see, are each of my individual rates, which rate is bigger. And oftentimes it's actually going to be easier to look at these two on a graph and just look at the graph and see which one is bigger. We can also ask, when are the rates equal? Well, to figure out when the rates are equal, you would set them equal. So you would graph the rate in, and you would graph the rate out. And actually we would graph these in like y1, and the rate out you would graph in y2, and then we would find the intersection of y1 equaling y2, and that would be the place where the rates are equal. All this talk of increasing and decreasing, we can also find when we have a maximum or a minimum amount of stuff And almost 99% of the times, these are going to be absolute maxes or mins because we are dealing with a time interval. All right? So recall that if you have to deal with an absolute max or a min or a max or a min on a time interval, this implies that you need to do the candidates test. That's test. Woohoo! All right, so what's the candidates test? Well, we have candidates, and those candidates are time values. So we would have the start time and the end time, and then these things. And what are those things? Well, those would be like the critical times or critical values. And when would you find critical times? Well, you would find critical times where the net rate is 0. Oh, we just did that. You would find where the rate in was equal to the rate out. And those time values, however many there were, those would be your other candidates. Then you would find the amount at each time. Well, what's the formula for amount? You would do amount equals the start value plus the integral of the rate in dt, oops, we'll make that in blue, minus the integral of the rate out dt. And you would integrate these from the start value, the starting time, start t, to whatever time value you had over here. So if these were the yellow t values, you would integrate to the yellow t values of your start time, your end time, and the middle t value, whatever critical times you had, and that's how you would calculate those amounts, and then based on that you would pick the biggest and smallest ones, and we'll see some examples of that in an example video. Just to give you a visual, let's say you did have a bucket, okay, and you had some water in it, woo, water, yay, and you had like a fire hose that was just gushing water into this, and then you had a tiny little thing here, and only a little bit of water was leaking out. What would happen to the amount of water in here? Well, the amount of water would increase, because clearly the rate in is far greater than the rate out. Okay? But let's say that over time, your fire hose slowly lost strength and, then went to a small fire hose going in. Okay? And then, I don't know, maybe you decided to drill a bigger hole in this, so now it was like a greater hole. Okay? When these two rates are equal is when the water level would sort of stop rising and then start falling, when the rate in was equal to the rate out. Because once the rate out is bigger and more water begins gushing out, then the amount of water will start decreasing. So if the rate in minus the rate out goes from like positive to negative, then we would have this sort of relative maximum behavior, where if you had the net rate being positive, then the amount would be increasing, and if the net rate was negative, then the amount would be decreasing, and look at that. That looks like the fun chart because it's basically describing how the amount changes based on the rate. And then the last thing we might ask is, what does like r the rate in prime mean? Which is kind of a weird question because the rate in sort of already is the derivative of the amount, but this is it's the rate at which the rate is changing. So in a sentence, this would be the rate at which the rate in is changing. Okay, so if we look at our like bank analogy, right? My rate in, oops, what is that? The rate in is sort of like my annual salary. Yeah, sure, all like $0 of it. But then the rate at which my salary changes, that's sort of like every year I get a slight increase. And so like my rate prime would be the increase in salary every year. Or if we go back to the water analogy, I would have water coming in, but if I were to slowly like turn that hose off and over time the rate was getting smaller, sure, I'm still adding water in, but I'm adding water in at a slower rate, and the r prime describes that.